Yes, you can actually time travel. In this video, I will show you how it works, explain the math behind it, teach you a 2-second calculation you can do yourself, and give you a real-life example that proves time travel is real. And at the end, there is a simple quiz to test yourself if you actually got it. On the most basic level, imagine a diagram with a north and east axis. You can choose to drive only north. In that case, you have no movement east, only north. But if you turn slightly toward the east while driving north, you are now moving northeast. This means you're still moving north, but less than before. If you drive entirely east, you are no longer moving north at all. You are moving only east. Now, let's replace north with time and east with space, creating a space-time diagram. In real life, it's not as simple as just moving east or north, but the concept still applies. Here as well, you can only move through time, like what you're doing right now, as you're sitting still watching this video. You're only experiencing time, but as soon as you start moving through space, your motion through time becomes less pure. It's now tilted slightly toward the space axis. The faster you move through space, the less you are moving through time. This means your experience of time slows down. If you were to somehow reach a speed where all your motion is in the space direction, your motion through time would become zero. Time would stop for you. Sad news is, objects with mass, like humans, cannot reach that speed. But that's a topic for another video. So as you move, no matter how fast, your time ticks slower, and it can be proven with a very simple math. As I explained in the previous video, Einstein in the second postulate of special relativity said that speed of light is always constant and it always c. So how does time dilation and time travel come out of this statement? Well, imagine we have two people, Bob and Emily. Bob gets in his spaceship and flies away while Emily stays on Earth watching Bob traveling through space with his spaceship. Bob has a light clock which has two mirrors with a light beam bouncing between the two mirrors. So this is from Bob's frame of reference. But Emily sees the whole thing differently. Since the spaceship is moving, she sees that instead of simple vertical path, the light beam of the light clock travels this diagonal path, which means greater distance. Since we know we can calculate distance by multiplying time by speed, we can rearrange things in the formula and get the time formula, which is time equals distance divided by speed. So in Bob's case, the time, let's name his time TB, B for Bob, is equal to D divided by C. But what about time in Emily's point of reference? Since from her point of reference, this is the path that the light took, we can easily calculate the S by using Pythagorean theorem. S squared equals D squared plus L squared. So S equals the square root of D squared plus L squared. This is a distance that the light has traveled. Now that we have the distance in Emily's case, we can do the same thing we did with Bob. TE, again E for Emily, is equal to square root of D squared plus L squared divided by C. So Einstein said that C, the speed of light, is always constant. Now we have two scenarios, where in one, light has traveled more distance compared to other scenario, even though the speed in both is the same. That means that the light that has traveled a greater distance should have traveled for a longer time. Because whenever we multiply the subject by denominator, we get the numerator. So both denominators are the same, but the numerators are not. Meaning in order to get the correct numerator, the value of the subject should change, resulting that the time for Bob passed differently for Emily. The fun part is we can calculate exactly how differently. So here, in Emily's perspective, the white line represents the distance that the spaceship has traveled as the light beam completes the half cycle. As we said earlier, distance is equal to speed multiplied by time. So V times TE. So here's what we have: TB, TE, and L. In TE, we know that L equals VTE. So we can substitute L with VTE. Next, we squared the entire equation to eliminate the square root on the right side. Then we move V squared over C squared multiplied by TE squared to other side of the equation. Now you can see on the right side remains D squared divided by C squared. That kinda looks familiar. TB is also D over C. So we can substitute D squared over C squared with TB squared. If we look at the left side of the equation, we can factor out TE squared. Then we divide both sides of the equation by 1 minus V squared over C squared. Finally, to solve for TE, we take the square root of both sides. We end up with this, the time dilation equation. With this, you can calculate how much someone has traveled into the future every time they move. This formula comes from the Lorentz transformation that gives you the ratio between two reference frames, and then you can use it to calculate the time dilation, length contraction, and mass contraction. Okay, now that we have this formula, how do we use it? Again, let's imagine we have two twins. One gets in a spaceship and goes to explore for 10 years with 80% of speed of light, while the other twin stays on Earth. After 10 years, how many years have passed for another twin on Earth? So we can easily use the time dilation equation, and it comes around 16.7 years. By the way, I made a video about how you benefit from this equation every day and you don't even know about it. To watch that video, join the community for free. Link in the bio. Okay, now that we proved it mathematically, let's talk about a real-life proof. Every second, tons of cosmic rays crash into the Earth's atmosphere. After colliding with air molecules, they break into fundamental particles, or better said, subatomic particles, like electrons, protons, and many others. These particles travel at 99.99% of the speed of light. We can't detect them because we have detectors on Earth's surface. One of these particles that we detect is called muon. Detecting muon is fascinating because in theory, we shouldn't be able to. Why? Because muon have a lifespan of only 2.2 microseconds before they decay into another subatomic particles. 2.2 microseconds is simply not long enough for them to travel the distance from the upper atmosphere to Earth's surface, even when moving at 99.99% of speed of light. At that speed, they could only travel about 600 meters. Far short for the 20 kilometers they need to cover to reach Earth's surface. So how do they manage to reach Earth's surface? If we apply the time dilation equation, we can calculate how much time would pass from our perspective while muon is moving. The result is about 155.6 microseconds, which results in 46 kilometers distance travel, more than enough for the muon to reach Earth's surface. This is one of the best real-life examples of time dilation. The only reason we can detect these muons is that time runs slower for them from our perspective, because they are moving at almost the speed of light. From the muon's perspective, its lifespan is still 2.2 microseconds, but due to time dilation, from our perspective, it lives long enough to reach Earth's surface. Okay, are you ready to see if you actually understood time dilation? Here's a real-life situation. This is Jeff. He's an astronaut. He's going on a 6-month mission to the ISS. The ISS orbits around the Earth at 28,000 kilometers per hour. When he returns, how much older will his kids be compared to him? Comment down below with the answer and I will like the correct ones.